talk about bone development, and then we'll talk about bone remodeling. And then the last one will tie up the loose ends, the last lecture. So ossification or osteogenesis is the process by which bone tissue is formed. Formation of the bony skeleton starts within the second month of development. Postnatal bone growth occurs until early adulthood, but then that still continues with remodeling and repair throughout our life. So about 8 weeks, fibrous membranes and hyaline cartilage of the fetal skull are replaced with bone tissue. So there are two different ways we can make bone. There is endochondral ossification, which is probably the more common type. Bones are formed by starting with a hyaline cartilage model, that is the shape you want the bone to be, and then replacing that hyaline cartilage with bone tissue. And the bones that are formed this way are called cartilage or endochondral bones, and most of the skeleton is formed in this way. Most of the time when we grow bone, we put down a hyaline cartilage model and then replace that model with bone tissue. The fibrous or the flat bones don't usually work that way, though. For those, we have a different system. We still use a model that's the right shape, but that model is formed from a fibrous membrane. So this is referred to as intramembranous ossification. And bones that are formed in this way are called membrane bones. So we've got two basic types of bones, endochondral and membrane bones, and most of the bones are endochondral. Essentially all the bones inferior to the base of the skull, with the exception of the clavicles, are endochondral bones formed by endochondral ossification. So they start with a hyaline cartilage model. The process for this begins in month 2 of development. It's going to use, again, previously formed hyaline cartilage models. Requires the breakdown of the hyaline cartilage prior to ossification. It starts at a location called the primary ossification center in the center of the shaft, where blood vessels infiltrate perichondrium, convert it to periosteum, mesenchymal cells that are going to come in and specialize into osteoblasts. There are about 5 steps to the process. We can outline it in 5 steps. Bone collar will form around the diaphysis of the cartilage model. Central cartilage in the diaphysis will then calcify and then develop the cavities. Periosteal bud will invade the cavities, leading to the formation of spongy bone. So the bud is made up of blood vessels, nerves, red marrow, osteogenic cells, and osteoclasts. Diaphysis will then elongate and the medullary cavity will form. That will lead to secondary ossification centers appearing in the ends, the epiphyses. The epiphyses would then ossify as hyaline cartilage remains only in the epiphyseal plate and on the articulate cartilages. So we start with step number 1, primary ossification. We get cartilage calcifying in the center and the cavity developing, infiltration of blood vessels, nerves, and so on, until we end up with a bone that is as we would expect for a long bone. For intramembranous ossification, we start with a fibrous connective tissue membrane, and those membranes are formed by mesenchymal cells. We just talked about mesenchymal cells and endochondral ossification. This is how we're going to form the frontal, parietal, occipital, temporal, and clavicle bones. So the frontal, parietal, occipital, and temporal are all skull bones, while the clavicle bones are found in your appendicular skeleton. Here we have 4 major steps. Ossification centers formed when the mesenchymal cells cluster and become osteoblasts. Osteoid is secreted, then calcified. Woven bone is formed when the osteoid is laid down around the blood vessels, giving us the trabeculi. Outer layer is going to form periosteum. Lamellar bone replaces woven bone, and red marrow would begin to appear. So here we have an ossification center developing, spreading out until we get the trabeculi and then compact bone on the edges. After birth, the long bones grow lengthwise by interstitial or longitudinal growth of the epiphyseal plates. Bones increase in thickness as well through appositional growth. They stop growing during adolescence, but there are some facial bones that can continue to grow slowly throughout life. So in long bones, we get the epiphyseal cartilage giving us interstitial growth, and that involves the epiphyseal plate. The epiphyseal plate maintains a constant thickness. The rate of cartilage growth on one side is balanced by bone replacement on the other side. So our epiphyseal plate can be divided into 5 zones: resting, proliferation, hypertrophic, calcification, and ossification zones. So the resting may also be called quiescent. Proliferation is where growth of the cartilage is occurring. The hypertrophic zone is just below that. Below that, it's becoming calcified, and below that, it's becoming more bone-like. So the area of cartilage on the epiphyseal side of the epiphyseal plate that is relatively inactive is called the quiescent or resting zone. Just below that is an area of cartilage on the diaphyse side of the epiphyseal plate, rapidly dividing. The new cells are formed and move upward, pushing the epiphysis away from the diaphyse, which gives us the lengthening of the bone. Then we have an area with older chondrocytes closer to the diaphyse. Their cartilage lacunae are enlarged and erode. They're forming interconnecting spaces in the hypertrophic zone. Below that is the calcification zone. As the cartilage matrix calcifies, chondrocytes die and deteriorate. And then we have the ossification zone, where the chondrocyte deterioration leaves long spicules of calcified cartilage at the epiphyse-diaphyse junction. Those spicules are then eroded by osteoclasts, then are covered with new bone, osteoblast, and ultimately replaced with spongy bone. Eventually, the medullary cavity enlarges as the spicules are eroded. Near the end of adolescence, the chondroblasts begin to divide less often. The epiphyseal plate thins and eventually is entirely replaced by bone, leaving the epiphyseal closure, which we just refer to as the epiphyseal line. In females, this happens around 18 years of age. In males, around 21 years of age. Growing bones are also wider as they grow. This occurs through appositional growth, and this type of growth can occur throughout our lives. The bones will thicken in response to increased stresses from muscle activity or added weight. Osteoblasts beneath the periosteum will begin to secrete bone matrix on the external bone. The osteoclasts will remove bone on the endosteal surface, usually more building up than breaking down, which will lead to thicker, stronger bone that is not too heavy. This whole process is under the control of hormones, largely. Growth hormone is the most important in stimulating epiphyseal plate activity in infancy and childhood. Thyroid hormone modulates activity of growth hormone, ensuring proper proportions. Testosterone and estrogens in males and females at puberty promote adolescent growth spurts, and they also end growth by inducing the closure of the epiphyseal plates. But excesses or deficits of a hormone can lead to abnormal skeletal growth. And then we'll talk about remodeling. So once we've got our bones, throughout life, as we use them and apply stresses to them or take stresses away, we're going to reshape our bones in a process called bone remodeling. About 5 to 7% of bone mass is recycled each week. Spongy bone is replaced every 3 to 4 years, while compact bone replaced every 10 years or so. Bone remodeling consists of both bone deposit and bone reabsorption. It occurs at the surfaces of both periosteum and endosteum. So an individual remodeling unit would be packets of adjacent osteoblasts and osteoclasts that are coordinating the remodeling process, blasts laying down, clasts breaking down. Reabsorption is the function of osteoclasts. They dig depressions or grooves as they break down the matrix. They secrete lysosomal enzymes and protons, so an acidic environment that digests the matrix, and that acidity helps convert the calcium salts into soluble forms of calcium so that they can be picked up by the bloodstream and used where they are needed. Osteoclasts also phagocytize or eat demineralized matrix and dead osteocytes. The digested products are then transcytosed, moved across the cell, and released into the interstitial fluid and into the blood. Once the reabsorption is complete, osteoclasts undergo apoptosis and commit suicide, if you don't know what apoptosis means. Osteoclast activation involves the hormone parathyroid hormone, as well as T cells proteins from our immune system. New bone would be deposited by osteoblasts. There are structures such as the osteoid seam, which is a band of unmineralized bone matrix that marks the new area. Calcification front is a transition zone between the osteoid seam and older mineralized bone. Triggers for deposit may include mechanical signals, increased concentration of calcium and phosphate ions for hydroxyapatite formation, matrix proteins that bind and concentrate calcium, and an appropriate amount of the enzyme alkaline phosphatase for mineralization. Controlling remodeling is, even though it's going on all the time, regulated by genetic factors and a couple of control loops. So the hormonal controls would be a negative feedback loop that's going to help to control calcium levels in the blood. Calcium has many important functions in the blood, many important functions in the body, aside from forming bone, things that are immediately dangerous to our survival, like nerve transmission, muscle contraction, blood coagulation, nerve gland secretion, cell division. But about 99% of our calcium is found in our bones. Intestinal absorption of calcium also requires vitamin D. The other control is a response to mechanical stress. Parathyroid hormone is produced by the parathyroid gland in response to low calcium levels in the blood. It stimulates osteoclasts to reabsorb more bone. As that bone is reabsorbed, the calcium is released into the blood, raising blood calcium levels. And parathyroid hormone secretion would stop as soon as a homeostatic level of calcium is found again in the blood. There is another hormone produced by the parafollicular cells of the thyroid gland called calcitonin. Its role is really not that well understood. Parathyroid hormone definitely regulated by low calcium in the blood. High calcium and calcitonin, the link is much more tenuous. But it's produced by the parafollicular cells of the thyroid gland, and it can activate osteoblasts, giving us our typical teeter-totter of homeostatic imbalance. So calcium drops in the blood, parathyroid cells release parathyroid hormone. Parathyroid hormone activates osteoclasts. Osteoclasts break down bone, and calcium goes back up. So even small changes in blood calcium can cause severe neuromuscular problems. Low calcium causes hyperexcitability of neurons for reasons conditions we'll get into in a few chapters. Hypercalcemia, hypocalcemia causes hyperexcitability, and hypercalcemia will cause non-responsiveness. So sustained high blood calcium levels can also lead to deposits of calcium salts in blood vessels or kidneys, leading to the formation of kidney stones. So some of the hormones that play a role in bone density and turnover include leptin, a hormone released by adipose tissue, as first function was to turn off appetite in the brain, but it also has a role in bone density. And it may do so by inhibiting osteoblasts. Serotonin is a neurotransmitter that regulates mood and sleep. It also interferes with osteoblast activity. Even though it's a neurotransmitter, it may surprise you to know that most serotonin is made in the gut. It's secreted into the blood after a meal, and that may inhibit bone turnover after a meal so that calcium can remain in the bones if there's new calcium coming in from the diet. Response to stresses. Bones reflect the stresses they encounter. Bones are stressed when weight bears on them or muscles pull on them. And there is something called Wolff's Law that helps to explain that. Wolff's Law states that bones grow or remodel in response to the demands that are put on them. The stress on a bone is usually off-center, so bones tend to bend, and that bending compresses one side and stretches the other. So a diaphysis is thickest where the bending stresses are greatest. The bone can be hollow because compression and tension cancel each other out in the center of the bone. Hollowness makes them even stronger. So here is a diagram of this Wolff's Law. Bones shaped in response to stresses. Wolff's Law also explains why your handedness results in thicker and stronger bones on the corresponding upper limb. So if you're right-handed, your right arm is thicker and stronger than your left. Also explains why curved bones are thickest where they're most likely to buckle. Trabeculi are going to form trusses along the lines of stress. Their large bony projections occur where heavy active muscles attach, so weightlifters have enormous thickenings at muscle attachment sites for those that they are using to lift the muscles. But it also means that bones of the fetus and people who are bedridden do not have those strong features because they have the lack of stress on those bones. So Wolff's Law, an important law think about in bone remodeling. Mechanical stresses produce slight electrical signals when bone is deformed. Hormonal controls will help determine if remodeling occurs in response to calcium levels. Mechanical stresses, though, determine where that remodeling occurs. All right, let's break her off there.